Thank you for joining Once Changing the World, India's first Future Tech Meets Sustainability podcast. I'm your host, Eddie Abel, and today I'm delighted and honored to have with me Professor Sreetosh Goswami, an SSc professor at the Center of Nanoscience and Engineering at the Indian Institute of Science, Bangalore. Professor Sreetosh obtained his PhD from the National University of Singapore. His contributions have been recognized with several national and international accolades, and his research areas are design of brain-inspired computing devices, electronic and ionic non-linear dynamics in molecular memristors, ultra-low energy electrical switching devices, nano-optoelectronics using molecular thin films, in situ Raman and absorption spectroscopy. Professor Sreetosh has recently led a team from the IISc to create or develop a brain on a chip capable of storing and processing data in 16,500 states within a molecular form. So today the topic of our discussion is going to be a leap forward in AI, India's brain on a chip technology. So Professor, really appreciate you taking time and being part of the podcast.
Thank you for having me.
Thank you. So, recently, obviously, AI is in the hype cycle. We've seen, the rapid advancement of, AI technologies, LLMs, chatbots. But along with its advancement, we're also seeing these growing concerns, about the immense energy that it takes and, the data requirements also, with the training and the deployment of these models. What do you see as the primary roadblocks to developing AI or artificial general intelligence that we are working towards in a sustainable manner? And how does your research address these challenges?
Sure. So I think other than the energy issues, there is one more issue which probably I'll try to add here. That is data privacy. That's another concern that has been there for a while, and it is increasing. So yeah, as you said, that energy requirement and the data privacy, these are the two primary concerns of AI. Now, if I go for the problem that we have in current AI, in one word, if I can say, that is the hardware. Because if you see how we are doing AI is, we have our computers, existing computers. And to be very honest, these were not designed for AI. These were designed for something else. Now, as AI came along, what we had algorithms which were supposed to do certain operations, which were supposed to learn from its environment, if I put it very simply. But our computing hardwares were designed for precision computing, how accurately you can multiply two numbers, or how accurately you get an answer to a problem, which is very deterministic. Now, when it comes to intelligence, the answers do not need to be absolutely deterministic. So there are less accurate answers. There are scope for that. And you necessarily do not need absolute precision. What you need is perception. So these hardwares are not made for that. As a result, what you do is when you try to do these algorithms, run these algorithms in these type of hardwares, there are two consequences. One is these are time and energy taking. So these are inefficient on these two fronts. And the other thing is most intensive part of these algorithms, if you see, they are actually done at the cloud. So basically at the data centers, which are owned by certain big corporations. So almost all of your, probably not all, but a major fraction of your personal data gets sacrificed to run most of the major AI models. So these are the two challenges. In terms of energy also, if you see these data back and forth between your personalized devices and the data centers, this is the part which consumes the maximum energy. So if we can reduce this, then your energy efficiency will grow up dramatically. And I mean, there are scary predictions that by 2040, we might not have enough energy to feed computing. These things exist. We don't know when it actually will happen. It might be much farther than what is anticipated. It must be much earlier than what is anticipated, because we don't really know that how AI will transform all the industries. So that's where we stand now.
Fair enough. So, you rightfully pointed out, I think AI currently, I think it's upended society with its kind of utility that is provided. But at the back end, you see that it's got a lot of these deep issues or problems that still needs to be sorted. You mentioned, I mean, not just the energy, but you also about the data privacy. Yes, because I mean, today I think most of these LLMs are crawling the net for our data, and that's what it's being trained on. So there is obviously these LLMs. It's has its problems, but there are those researchers at the forefront, who believe in this model. They think that scaling is the only challenge over there, and you brute force, more data, more energy, and their assumption is that maybe that could lead to artificial intelligence. While there's the other side, that who are these neuroscientists and who believe that our brain is nowhere close to these LLMs because they consume just 2 watts of energy, and they don't
20
need,
watts.
20 watts of energy, and they don't need these humongous data that these LLMs today require. So there's this concept of, like a brain inspired computing, a neuromorphic computing. Would you be able to kind of like broadly, possibly first maybe explain what this neuromorphic computing is, and also then maybe the brain on a chip that you are working at IISc, and maybe
Sure.
also the like explain how it's different from a traditional computing system.
Sure. The thing is, as you rightly pointed out, that brain taking inspiration from brain for the obvious reasons that 20 watt and humongous amount of power that data centers consume, that idea has been around for a while now. Even in 1980s, there had been scientists who proposed brain-inspired computing. But the point is that those days, this was more like a blue sky research. And it was not even clear that whether you need that kind of new computing for the application that was relevant at that time. With the advent of artificial intelligence, it just became more and more prominent. Now, when I say brain-inspired computing, I think I would like to clarify first one thing. The question is, what is brain-inspired computing? Are we trying to make a brain? At least I probably should not talk about the whole community, but at least if you ask me, from my perspective, I don't think I even remotely understand what a biological brain does. I am nowhere close. So the point is that whatever bits and pieces we understand the brain, from that can we take inspiration and make a better computer than what we have today? That is what brain-inspired computing is. So it's a step forward in terms of the computing technology to enable artificial intelligence and many other forms. So it's clear that it is not that only if you make a better brain-inspired computing platform, it is not only the artificial intelligence that is going to be benefited. You can use that in many other applications. It can be signal image processing. It can be many different things in computing. So the point is where we take the inspiration from. Now, these inspirations are very loose and segmented. For example, I'll give just, of many others, I'll take one example. If you take a traditional computer where it stores the data and where it does the computation, these are two physically segmented locations. One is the processor and the other one is the memory. And the way you do it, you store the data somewhere, and then as and when you need the data for the computation, you route it from the memory, do the computation, and then store it back. And again, when you need the thing, you again fetch it. So this data back and forth consumes a lot of energy. So the thing is, if you see the history of brain-inspired computing, big tech giants like IBM, Intel, they had been trying to make brain-inspired computers since 2010, around that time. There are bold predictions that they made that within a certain time, they might be able to emulate brain and within a box of few liters. But the point is, none of these predictions had come to a reality. The primary reason is that what they did is it's a brute force attempt. Probably in the process, we also realized that how complex actually brain is and how much underestimation that was done in those predictions. But the main thing is the digital computers, if you take which has two states, 0 and 1, you can impose any algorithm you want at the software level. But that brute force attempt just doesn't work because it has been done and tested. So unlike most of the technological progresses where it usually goes from the academia to industries, what we saw here is from industries tried the brain-inspired computers. And after that, there is a surge in investments in the academia because people understand that brain-inspired computing is very promising. But the problem is that we don't have the materials, we don't have the devices, we don't have the architectures. So this is a point where we realize that we need to reinvent several stages of computing. It's a co-development at the fundamental level, at an architecture level, at a systems level, at every level, because brain is inherently different. So taking inspiration from those, one of the things that we do, for example, is can we compute where we are storing the data? So that is one example. So that is something called an in-memory computing. So you don't take the data from memory to the processor, but you do the computation where you are storing the data. Now, another level of complexity can be, now say you are doing it with two states, 0 and 1, still doing it digitally. The next point is, can we do it in multiple states? Now, if you see synapse, for example, in our brain, it can store data in many levels. Now, this is where it comes that whether we can store this data in as many levels as possible and do computations using those. So that has been another aspect of brain-inspired computing. At the end of the day, the main thing is that whether in these processes, whatever we do, if we make an accelerator or a computing platform which can do much better than something that exists, and the other thing is it should be integrable to the platforms that exist today. I mean, one can always say that I will revamp almost everything, but that's very unlikely to happen in our lifetime. So silicon technology is very mature; it will be there. The point would be whether we can come up with something which can actually augment it. So we can think it as an add-on, and that can augment a lot of computational efficiencies. So that's probably the right way to look into the brain-inspired computing, at least to my view.
Right. Yeah. Yes. So I think there's quite a lot of things that you said over here. You mentioned that we don't understand the brain. I hope that we come to a point maybe in the near future where we do understand the brain, because I mean I do get to speak to a lot of neuroscientists, neurotech researchers, and everybody's got a very varied response on the understanding of the human brain, because there are some who believe that yes, we know a little bit of how the brain functions, while then there are others who say we don't know anything. Now, where do you guys stand currently, with this brain on a chip technology? You mentioned you're leveraging in-memory computation and possibly maybe emulating a synapse where, instead of storing the zeros and ones, you're storing in many states. And you in the news clip of it says that it can store somewhere around 16,500 states. Elaborate on this. I mean, and what are you actually leveraging for it? I mean, it's a molecular memristor, right? Will be great if you could, talk about.
Sure.
Yeah.
Sure. So one thing probably before I go into the specific things that we are doing, understanding of brain is probably something, as you say, that it is, many say that it is, people are making progress in it. There is no question about it. But if as someone who wants to make an electronic circuit out of it or a computing platform out of it, it's about we need to understand that to what extent we need the clarity. So one is qualitatively saying that how brain is working. The otherwise, if you want to make a circuit, you need equations. You need mathematical equations to actually model how certain things operate. That's not easy. So unless we have a mathematical model, it is very difficult for us to make circuits. And that is why the connections are still very loose. Okay, so that's one aspect. The second thing I just wanted to stress on is it's as you said that it's a molecular memristor. So molecular memristor means that it's basically a film, molecular film in between two electrodes. The thickness of the film varies, but you can say it's like 50 nanometers, for example. So as you apply electric field, there are molecules and ions inside the film, and there are different orientation and charge states within these molecules and ions that are possible. And this is just not about 0 and 1. If you imagine that there are 1 million molecules between the two electrodes, then as you apply the voltage, you can create different combinations of electronic and morphological states within the film. And each of these different states will give you different current signals. So the main idea is that how many such states we can stabilize and store data in and subsequently do computations with. In the paper that we were talking about that came in Nature a couple of weeks back, so what we could do is we found a sweet regime where using I would say a very small we operated in a small perturbation regime. And within that, we were able to stabilize 16,500 different levels. Now, say to be precise, it is 6,520 levels. Now, the idea is that what differs from digital to analog is in digital computing, although you operate in 0 and 1, if you want to express numbers, say from 1 to 16,520, you will still can do it, but you will require multiple bits. So it's like a string of zeros and ones that will store that number. In contrast, in this case, all you need is just one small element which has so many levels. So other than having that string of bits, here you can store it in just one nano element. So as you can see that it spatially it's very much quenched. And then as you can also see that rather than having 14 such lines, 14 such bits, here you have just one line and from one circuit element. So that reduces both the footprint and the energy. I mean, that's probably very, to put it very simply.
So what was that insight of yours that made you go for this nanomaterial, which you thought, can possibly mimic like what the brain does, and maybe talk about the other challenges, maybe what you and your team faced developing this brain on a chip tech.
Oh, this molecular research that we are doing, this is something we had been doing for the last 10 years. So it didn't come on a sudden. The question that we started asking 10 years back was if you take such molecules, so if you just consider molecules inside a beaker, and if you just put it in a film of 50 nanometer, and then you apply electric field, their behaviors are completely different. So the questions that we asked at that point was if we put it in such a nano-sized structure and subject it to electric field, what kind of changes we might expect to see? So there might be electronic state change, there might be geometric change, there might be structural change, there can be change in the morphology, There can be change in how the molecules interact with each other. There can be change between the molecules and ion interaction. So if I list the entire, what all changes can it cause, it's huge, right? So then the question is that how do we probe it down to the things that we can control and how we can vary the electrical responses. So for that, there are different sets of fundamental experiments that had gone into it. So first, which molecules you synthesize, because any random molecule will not do it. So this is where, if you see, it's a very interesting collaboration, because the class of compounds you see today, this is something that my father synthesized. So he's a inorganic chemist. So he had worked in different branches of chemistry where he used these metal organic complexes for his reactions, catalysis, and many other applications. The point was that he used to say that this is an electron sponge. That means that this is a molecule that can accept many electrons, and of course can give it when it is needed. Now the point is, since there are many electronic structures that were inherently possible, we tried to ask the question: okay, me being an electrical engineer, I don't understand many other things that the chemists would probably imagine doing, but the question is whether we can put it in between two electrodes, a very simple sandwich structure, and apply electric field and try to see that what it does. But what we saw is the moment we tried to do it, the responses were crazy. It was very difficult to understand it. And I still would say that right now, the stage where we are in, we probably, once we get a result, we try to make sense of it. If you say that, okay, in this molecular system, if you vary that unit, what will happen? That is the strategic prediction of the next molecular system. We still cannot do it. We are trying to do that. We at least understand that what kind of fundamental studies are required to do that. So that is one very important aspect of this research, that although it is a very technologically driven research, unless we understand the fundamental science, it would not drive it. And that is, in fact, one of the reasons why, if you come to my lab, there are actually two labs side by side. One where we make the circuits, and very next lab where we have a silent room. So it's inside that room, the noise level is less than 35 dB, which is extremely silent room. What we do is there we do something called a tip-enhanced Raman spectroscopy, where we apply electric field across a molecule. And then what we try to do is we try to get the Raman signal from individual molecules. So what it tells us is, if you are applying a field, then what kind of changes, what kind of electronic changes you try to see inside a molecular film like that. And that inspires the design of the devices. And once you have such devices, then it comes to the question that how can you make a complete array of such devices? Because one can always make a hero device and jump around with that and say that, okay, we made this. But that doesn't make any sense, because understanding it and making a hero device is one possible path of doing research. But if we have to do something meaningful, this needs to be scalable. We have to make thousands of such devices and make a circuit out of which is scalable. So that goes into the fabrication. So there are students who are working on that, who are translating such hero devices into circuits, which is what one of the aspects this paper covers, where we show that it can design a platform which can do certain useful operations. And then the point comes that, okay, we have a circuit of memristors. Can it be integrated to the silicon circuits? Because as I said, that one cannot topple silicon industry. It is billions and trillions of dollars have gone into this technology, and it's a very mature technology. So next comes the integration of this molecular technology with this circuits. And this is where I regularly collaborate with my colleagues, such as Professor Noah Kantuhat. he's an expert in silicon electronics. So we see that how this can be integrated with a silicon circuit and what kind of augmentation we can get out of it.
Right. Yeah. So maybe it will be great if you can talk about that. How do you kind of, integrate it with the silicon circuit? Maybe also talk about your team. And then you mentioned that, it should be able to do these useful operations. What do you think can it do right now? And once it gets integrated with like a silicon circuit, what could be done with this brain on a chip technology?
Yeah, so right now the way we are integrating is it's a simple integration, relatively simple integration. That is, we have a printed circuit board, and on top of that we just connect this chip, which is the molecular chip, and then do the operation, because a printed circuit board, PCB, what we call that, you can put a microcontroller with that and can connect it to a computer. You can do whatever you want. So the way this chip works is it's basically an analog platform. So you need to connect it to the external digital platform. So the board, existing silicon circuit is the medium for doing that interface. Now, what is a useful thing to do? Probably that's a very interesting question, because it will come down to one particular mathematical operation. That is matrix multiplication. So if you see almost all the computationally intensive tasks that we have today, I'll not say probably all, but majority of it, that involves matrix multiplication. If I just go chop it down a little bit more, then it would be vector matrix multiplication. Vector matrix multiplication means one of the rows of the matrix when you multiply to one column of the matrix. So it's just the vector matrix multiplication. So this mathematical operation is the foundation for all computations you see, starting from scientific computing, signal processing, AI, ML, you just name it. Thing is, this is a mathematical operation that consumes a huge amount of computational power and energy. That is because if you have a matrix of size n cross n, for doing a vector matrix multiplication, you need n square number of steps. So say if you have 10 cross 10 matrix, then you need 100 operations to do. Similarly, if you have 100 cross 100 matrix, then you need 10,000 number of operational steps to do it. Now, what our accelerator can do is take that vector matrix multiplication operation and do it in just one step. Okay. So your 10,000, for example, computational steps gets reduced to just one step. That clearly gives you a huge benefit in terms of computational time and as well as energy, right? Now, looking forward on it, the thing that needs to be done to make it useful, that is, what we have today is an integration to the printed circuit board, the PCB. What we need to do that is not going to cut it through. What we need to do in the future is there are silicon circuits that get made into the fabs, in different fabs around the world. You might be hearing about different technology nodes, 65 nanometer technology nodes, much lower than that we are going into, say right now, 7 nanometer technology node. So what we need to do is we need to take such a circuits which is made in one of the different fab units that is available, and then take it and then integrate our molecular technology on top of that. So then you would have a chip that is suitable for this, which is an accelerator that does vector matrix multiplication, and it is inherently integrated to what exists today, what industries can make today. And that can be used in, as I said, signal processing, that can be used for AI algorithms, that can be used in different sectors of bioinformatics. There are different aspects of it, yeah. So in the paper, if you see, what we did is, of course, it was not to put a very specific use case, but the point was that if you want to demonstrate a vector matrix multiplication and to show that it doesn't depend on the matrix structure, because why I say that is, if your matrix has certain symmetry or structures, you can apply many algorithms to make it simple. You can reduce the complexity. If your matrix does not have any structure, your vector and the matrices do not have any structure, you cannot do much. What can be more unstructured than space image? So what we did is we took a space image, took the data in frequency domain, and we did the entire image processing to develop the image of the pillars of creation, which was taken in the James Webb telescope, to actually show that it works. It works in the way, actually it worked in a way much better than we anticipated. So, yeah.
Right. Yeah. So yes, I was reading about in the newspaper that, how you created the pillars of a creation image just by using a basic computer. So congratulations. So, but what's the timelines that you give for, making this happen? And also maybe talk about the support system, what's being the support system over here? Because like, software industry, I think it's evolving. It's really, really cool. And there's, the government support system is there. But when it comes to hardware, what's the support system being there?
Yeah. So the timeline, I think for us, the timeline is 3 years. Within that, we are doing it, no matter what comes along. Because it's vital to put a timeline, because technology, if you see all the technological field, they are very fast growing. So unless we catch the train on time, then we will miss it. So that's the timeline. And the thing is, yeah, it's true that hardware has not been our strength in India. But the thing is, right now the support that we have is Ministry of Electronics and Information Technology, MITI. So the project is about how we integrate these molecular technology to the circuits that has been fabricated in industrial fabrication unit, which we call tape outs. So that is what we are doing. Government, as in the MITI, is supporting this initiative. But again, this is a point where to what extent can we push it? The answer is we can make proof of concept, what we call a system on a chip, to show that it does what we think it can do. We are already working towards different AI ML models. So in my view, probably one of the very critical aspects of this is bioinformatics. So for example, if there is a tool I don't want to go into specifics, but if there is a tool that can do the DNA sequencing, you do not want your DNA data to be shared with any of the big corporations. That's probably too personal. So the question is, can we design a AI-based platform which can help you in those? It's not really DNA sequencing. After DNA sequencing, using the technologies, you need to do a number of computational steps to actually make sense of it. Can we do those in your local devices? So can we do the AI training in your personalized devices? So these are the questions we are already asking. And along with that, parallelly, what we are doing is we are integrating it to the existing platforms, industrial tape outs, and that's where we are going. In terms of support, we have some support. It's a very tricky question. If I compare it with the global support, if you see the amount. I exactly don't know, but the amount of support that is available within even one university of China, that is probably 50 times what we have. So it's not a comparable thing, but what I would say that it is probably not minuscule as well, because of which we are able to do what we are doing. So it's a matter of where we want to push it. And also, so after this paper, there had been things that changed. We got approached by a number of different industries, people who can probably make differences in such ecosystems. Because if you see that, it's interesting that we do have the ecosystem for chip design. We do have ecosystem for the softwares. We need all of these to make a very successful AI chip. But what we probably do not have is a number of IPs which will give something which is very much indigenous technology, which is what we are developing. We are protecting these IPs and trying to leverage the expertise which are around in our ecosystem to do the best we can do.
Right. So, Professor, wish you and the team the very best, and maybe I'll hold you to that 3 years timeline that you mentioned, and maybe ping you again, maybe 27 and for a conversation update on where it stands, to if it's market ready at that point in time. And I wish, it is market ready, because I think AI, I think the world is completely woken up. The nations have woken up and understood the potential of developing AI, and obviously also indigenous systems, because, when we leverage a application which is from like another nation, then obviously we depend on them. So I think more power to you and, researchers and teams who are building indigenously over here, because I believe that if we solve this current problem with AI, which is extremely data hungry, extremely consumes a lot of power. And you mentioned about data privacy, all of these things, if we are able to solve with the approach that you guys are taking, I think we would get into a phenomenal world rather than in a dystopian world where we are all, there's no power for us, only the AI is consuming all the power. Who are the other peers you think who are working in the field and have taken the correct approach to build neuromorphic computing, neuromorphic chips?
There are multiple. So as you know that in science, it is never someone's. It's the approaches or the advancements are never standalone. It is always there are multiple threads to it. There are different material systems people had been using. Oxide systems people have been using. 2D materials have been another thread of research. Molecular systems, there are lots of people who are using that as well. So there are colleagues in the United States in different universities, spread across different universities, who are trying to develop their process. They are their accelerators for AI. I'm not taking specific names, which is probably will leave out many others. There are people in China. They have their own foundry just for neuromorphic computing. So that is probably on another scale. There is very notable progress made in Germany. There are a few colleagues even in Italy who are trying to do certain things, and in many other places. In India also, there are several laboratories who are making interesting progresses, and I think it's an interesting time to do computing, because if you see in the last 50 years, what we did is we developed new types of algorithms, but fundamentally computing hardware never changed. It's almost the same right now, because we are being hit back by the requirements. We are forced to change. So we are trying to rethink computing hardware at a very fundamental level. You can see that there are quantum computers coming. We are trying to do neuromorphic computing. There are different routes people are taking. Few people are working on spintronics. So the thing is, it will probably all come together to design a number of, it will never be one technology or the other. These technology will most probably coexist. And ultimately, what we will have, as we say, for AI, it will be a bunch of application-specific ICs, ASICs. So that will probably enable such AI systems. So yeah, there are many progresses that are happening today.
Right. Yeah, Professor, what advice would you give to young researchers interested in pursuing a career in neuromorphic computing or related fields?
Well, I don't know if I'm qualified enough to give advice to them. But of course, AI is probably the thing that would be that is inevitable. And interestingly, this is in this particular domain, everyone has a space. You start from chemists, you start physicists, electrical engineers, electronics, computer scientists, mechanical engineers. Everybody has something or the other to do. So the point is, it's so interdisciplinary that probably we should forget about what we studied. Not in the sense that what we studied, we should forget about what we studied. I mean, our disciplines. It should not be restricted to any of the disciplines. It should probably be like, we want to achieve this goal and we should try to get to that at any cost. I mean, for example, my background is electrical engineering. I did not know anything about chemistry. I came along, and when it was required, I learned it. Similarly, I have many physicist colleagues who regularly teach me different things, which is what we apply and take this forward. Similarly, to be honest, I never did circuit design, and when I talked to Navkant and several of his students, I regularly learn from them about how to do this circuit design. So it's a continuous process where we keep pushing. As long as we know the very fundamental things like +2 level physics, chemistry, or mathematics, I think everything can be self-learned. So that's probably what, at least I believe in, to the minimum extent that I can do. And still working.
Right. Professor, yes, I think it's so important to be a lifelong learner. I think the world has completely changed. Today we have these LLM models where it's almost like kind of upending or changing the world. It's added so much dimensions to or intellect or knowledge, and we being pushed into a world where I think being a lifelong learner is going to be so important. And the more you learn, the more you know, the more you will be able to do. And I think reaching out, interdisciplinary learning, I think is so very core. My last question to you:
Sure.
What are your views on AGI? You think the approach, this like just scaling up with more data or more compute, you think that would lead us to AGI? That's my first question. And yes, obviously, paint a picture of what maybe like the future is going to look like in the next possibly 5 to 10 years, when we have this billion-chip technology augmenting with our silicon circuits. You mentioned about, vector matrix multiplication, but possibly make it, spell it out that what those changes would be in society, how deeply society would be impacted once we have these neuromorphic computing.
Probably it's very difficult to predict these things. For example, this probably depends more on how this will be used. Whenever it comes to AGI, the thing is, AGI again, it's not a very well-defined thing. People are trying to develop it, but when it will actually be truly materialized, we don't know. And in AI, I think what is going to play a major role is the rules and the legal boundaries we create around it. Because the thing is, for example, a simple thing, this vector matrix multiplication you can use for making fake videos, you can use for detecting it. It really depends on what you want it for. So if you have this weapon in hand, it's always a double-edged sword. So you can use it the way you want. So as a person of my caliber who has no power, I cannot really portray a picture that what it will be used. But what we have seen from the history, that human nature is that partly it is used for good, partly it is used for bad. So more we prevent it from going into the bad ways, probably we can protect it. And on a good side of it, probably what I can imagine is you have your own local intelligence in all the phones and your computers. Probably they are so energy efficient that you charge it only once in a month. You can do a lot more than what is done today with the laptop. Probably what you are thinking, if you write few bullet points, it can generate the entire thing. So you don't need to think unnecessary to polish it, but think what is the crux of it, which is which are what the LLMs are supposed to learn and do. As one example, of course, it can have major impact in airborne vehicles. It can have in self-driving cars. Ultra high-tech society where smart buildings and everywhere it's so-called smart. But again, smart comes with a consequence. All your data is compromised. So there needs to be, again, a boundary that where the data is going. We need transparency. If everything is with the government or even an enterprise, government, we don't know how it is handled. If it is an enterprise, it's even worse. So the question is how the data will be managed. Those will be questions to ask, and there will be things which needs to be done on ethics front, on legalities, on what should be done and what should not be. So there needs to be a very clear mandate that needs to be laid out.
Thank you, Professor, for talking about both the good side as well as the bad side of technology. Technology inherently is never good or bad. It's basically when it goes into the hands of people who've got good intention, the technology goes into a good direction. Then we have these healthcare applications, and then it goes into the bad hands. Then we get into these deep fakes and technology for military and so on and so forth. So I think we need to be cognizant that for the first time in human history, all of the technology stack has become extremely potent, where maybe if it's might not be wrong to say that it's possibly, if not corrected right now, it could go out of the hands of the creators of this technology stack. Because even AI, where we've developed these LLMs, but some of the top researchers don't know what's going on under the hood. That's the reason we call it a black box AI. This tech stack is becoming growingly very, very potent. And it's not just AI, it's also quantum computing. There is immersive tech stack, which is augmented reality, virtual reality, mixed reality. There's nanotechnology, which you are vested in, and where Eric Drexler talks about the potential implications and great applications of nanotechnology, as well as the downsides, the gray goo, where possibly the gray goo could just take over a world. So, the businesses function with, profit at any cost. Every startup, every company, every government functions at that. But I hope that with this tech stack, the incentives are more somehow of creating like something which is like a better application. Because if it goes into the bad hands, the downsides, like you explained, can be completely catastrophic. And maybe it could also lead us to an existential crisis. And I hope that nations, institutions, people wake up and understand that we are now playing with fire. And this is in no term trying to be a fearmonger, because my last episode, when I was speaking with the chief economic advisor of the ex-chief economic advisor for the government of India, he thought that I was fearmongering. So just kind of bring this. In no sense, this is fear mongering, but to bring attention that we live in an exponential time. We are not in the linear time where tech moved in a linear trajectory. And these tech stacks, just like the brain and the chip on neuromorphic computing, like the kind of applications that it would bring into the world would be unimaginable. But yes, if it goes into the wrong hands, those applications itself could lead to an existential crisis. So thank you, Professor, for taking time and being part of the podcast. And my listeners, I hope you guys take this information and if you like what you see in here, then please don't forget to subscribe. Thank you, Professor, once again.
Thank you so much. Thank you so much.